Let me welcome you to this last lecture of our class in reinforcement learning at ASU. In this lecture, we're going to focus on offline training of cost functions and policies. We're going to pay some attention to approximation policy space, and particularly on policy gradient and random search methods. And we will wrap up the course. So here's the outline. We'll first discuss, in general, offline approximation and training of cost functions and policies. And then we're going to talk about three different training contexts. One is approximation of a target cost function that we are given and we want to approximate. The other is approximation of a target policy, which we're given again and we want to approximate. Then we're going to discuss direct policy optimization, whereby we consider a subset of policies parameterized, and we want to find the parameter that leads to good performance. And we're going to focus on policy grading and random search methods within this context. And then we're going to wrap up the course. So I'm going to try to summarize in one slide where we have been and what we're going to be doing in this class, in this lecture. We have viewed reinforcement learning as the art and science of solving optimal sequential decision problems approximately. Now, reinforcement learning deals with exactly the same mathematical problem as dynamic programming. Dynamic programming also deals with optimal sequential decision-making. So the two fields are very closely connected. And in dynamic programming, there are two major objects that we're interested in. One is cost functions or value functions, and the other is policies. So the field of reinforcement learning naturally divides along these two strands of approximation in value space and approximation in policy space. Now, we've talked quite a bit about approximation in value space so far, one-step and multi-step look-ahead optimization. And this line of methodology is connected with dynamic programming very strongly, the algorithms of value and policy iteration, rollout, and also there's an underlying framework based on Newton's method for solving the Bellman equation, which we have viewed as fundamental in this class without, of course, getting too much into the details. Now, the other strand deals with approximation in policy space. And it's not so much connected with dynamic programming. There is a connection with dynamic programming, but in terms of methodology, it's more connected with nonlinear programming and gradient type of optimization, and also with random search. Now, one characteristic difference about these two approaches is that in approximation in value space, there's a substantial amount of computation that you have to do online, okay? The one-step and multi-step look ahead with terminal cost approximation requires possibly a lot of computation online. On the other hand, approximation in policy space requires very little online computation. Once you train a policy, you just use it. Let's say your policy is represented by a neural network, then you just let the neural network decide on the action that you are going to apply at a given state, and that can be very quick, particularly in comparison with approximation value space. So there are some major advantages to this red line of methodology. On the other hand, we're going to argue that there are also some disadvantages, and that's going to be the focus of our lecture today. So let's talk about offline approximation and training in general. As I mentioned, there are two types of offline approximations in reinforcement learning. Cost approximation in the context of finite and infinite horizon problems, So we want to approximate the optimal cost function in a finite horizon setting or in an infinite horizon setting. We may also want to approximate Q factors, optimal Q factors in finite horizon and infinite horizon. We have focused on cost functions for the most part, and the methodology for training Q factors is pretty similar. So we're going to restrict ourselves to cost functions. The other cost approximation context involves the cost function of a policy, okay? A given policy for which we can train samples, training samples, for example, either non-stationary or stationary or finite horizon, infinite horizon, also the corresponding Q factors. And so that would be another possibility, optimal cost functions and cost functions of a given policy. Now, the other major type of offline approximation is when we approximate policies, both in finite and infinite horizon, so either an optimal policy or a given policy. And we're going to focus in this lecture on parametric approximations, approximations of cost functions that depend on a parameter R, and policies that also depend on a parameter R. And the idea is to find R that matches the target, okay, as best as possible. So these are functions of X that depend on the parameter R, and an example is neural networks, where R is the set of weights. That's a common parametric approximation architecture, neural networks with the parameter R being the set of weights. So now let's discuss the three contexts that we're going to focus on. The first one is approximation of a target cost function. So we have a cost function. We don't know its analytical form, its mathematical form, but we can get training data out of it. We can get pairs of X's and corresponding J values for a large number of samples. And then we use these to match an approximation architecture that depends on the parameter R, and get, after the training, we can get as approximating function this. So this one approximates this target by using the samples. And the training can be done with specialized optimization software, gradient type methods, and other types of least square methods that we're going to discuss later in this lecture. So that's our first context. The second context is approximation of the target policy. Similarly, we introduce a parametric approximation architecture that depends on a parameter R. Now, if the control has continuous components, okay, so the components of the control are scalars that take values over a continuum, then the training is pretty similar to the cost function case. It's just that this may be multidimensional, whereas J is one-dimensional. It's only one value for X and R. On the other hand, if the control comes from a finite control space, as in finite spaces MDP, then it's possible to adopt an alternative approach for a target policy. So we view the approximation as a classifier, the function that maps, we view a policy as a classifier, a function that maps X into a category, M sub X. In other words, a policy in this view is a black box that classifies objects into one of finite number of categories. The objects are the X's, the categories are the controls that you apply, okay? So with this view, we can use classification type of algorithms whereby we have this target policy, we generate training data from it, and the classifier is training, and then online it generates control probabilities. It generates a randomized policy, usually in classification. And these control probabilities represent the likelihood that the correct control is the corresponding mu tilde. Okay. So ideally, you would like these probabilities to be zeros, all zeros, and one, okay, a single control B1, but these classifiers usually give us a control probabilities, which can be converted to a 0-1 distribution by selecting the control of maximum probability. Now, the thing is that classifiers are somewhat different than neural networks, okay? They may involve a neural network, but they don't have to. And there's a range of software and methods that you can use within this context, assuming that the control space is finite. So this is a useful view to have in problems, that is this classification option. But if you have the target policy, a given policy, okay? Not finding an optimal policy, but approximating a given policy. First context, approximating a target function, cost function. Second context, approximation of a target policy. And the third context is direct policy optimization, whereby you introduce a parametrization of policies, and when you plug them into the system, they generate control in response to states, and they generate also costs. So each parameter value R defines a stationary and possibly randomized policy in case that these are a set of probabilities rather than a single control. Mu tilde R, so this is the parameterized policy, and its cost starting from a given initial state x0 is denoted like so. Now, this is a function for a given x. This is a function of R, and we can try to optimize this with respect to R. Find the parameter that gives you optimal cost. This is different than approximating a target policy. We have direct optimization with the parameters in the loop and try to figure out how to make them do good things. Now, this is for a single given initial state. If you're interested in multiple initial states, you may try to determine the parameter through minimizing a weighted sum of the costs for different states. And this corresponds to having a probability distribution over the initial state. So this problem and this problem are quite similar. Depending on the context, you may prefer one possibility or the other. So that's the third context. And now we're going to take these three contexts one at a time. First, target cost function approximation, then target policy approximation, then direct policy optimization. Okay, some generalities about parametric cost function approximation. We start with a parametric architecture. In other words, a class of functions that depend on state and on the parameter. The parameter vector has a number of components, M. M may be small or it may be very large, in the case of a deep neural network, for example. And these parameters are tunable. We can adjust them. And the training problem is to adjust the parameters so that J tilde, the cost function approximation, matches the training data that comes from the target function. And we can distinguish between different types of architectures. Architectures are called linear or nonlinear if this function here is linear or nonlinear in R, okay? And another categorization is when architectures are feature-based, which is if they depend on X via a feature vector phi, a vector, a multidimensional vector of the state, which captures major characteristics of A, X. And a feature-based architecture is one for which J tilde depends on X through the features, okay? In other words, there's another function, J hat, which is a function of the features, and R, and that gives you the approximation architecture. Now, the intuitive idea here is that good features can capture the dominant nonlinearities of the target function, and then we can afford to make this J hat simple. All the difficult stuff, the nonlinearities in this cost function, in this target cost function, are captured by the features. So J hat can be simple, and in particular, we can make J hat to be linear. Linear a weighted sum of the features of the state. RL are the weights, RL are the parameters. And J tilde has this form. In other words, is the inner product of the R vector with the feature vector. RL is the Lth weight that weighs the Lth feature. Okay, so my RJ hat is this linear function, and here we hope and expect that that the features will capture the dominant nonlinearity in J tilde. So the schematic diagram for this kind of linear feature-based architecture is that the state is, for a given state, we extract its feature vector, and then we linearly weigh the feature vector to obtain the approximation. Okay? So let me give you a simple example of a linear feature-based architecture, a piecewise constant approximation. Here is X, here's the approximation, it's piecewise constant, and it is a weighted sum of features. And what are the features here? Well, we partition the state space into subsets, S1 up to Sm, and the Lth feature is defined by membership in the corresponding set. In other words, the Lth feature is the indicator function. 1 if X belongs to this set, 0 otherwise. Now we weigh these features with parameters RL, and we obtain each one of these terms is a term like this. The 0, 1 indicator function multiplied with a corresponding weight. So each one of these segments of the piecewise linear function corresponds to a single feature. And that's a very simple linear feature-based architecture. Now, oftentimes, in a given problem, there are some features that stand out. Through some understanding into the problem, we can see what the features should be. And here's an example. Chess, here's the state, the chess position. We can extract features from the state. And these are quantities and characteristics of the position that chess players recognize readily, like the material balance of the position, the mobility of the pieces, the safety of the king, strategic features like open files and so on. Usually there are like 30, 40, 50 features that we can extract from a given position. It's subjective which ones you use, of course. And then we use a linear weighting of these features to obtain a position evaluation. That's the classical method of position evaluation in chess, okay? Up until the AlphaZero came along, which used a neural network in here. The classical method for evaluating positions in chess was this: manually computed, manually delineated features and weighted by parameters that were experimentally obtained. We play a chess game that we lose badly. We look, what's the weight that's responsible for this? Okay, let's fix that weight by increasing it, decreasing it, and so on. Another game that has been tested extensively, it has a long history. There's a case study of that in my neurodynamic programming book in '96, is Tetris, which is challenging and also stochastic. And in Tetris, okay, if you know the game of Tetris, we've been through this before, there are some obvious features of the position, namely the board position here. Features like the height of the columns, the difference between heights of adjacent columns is a feature. The number of holes in the board is a feature. The distance from the top of the board the distance from losing, okay? That's also a feature. And there are, in the standard implementation, are 22 features, a small number. And good performance has been obtained with this kind of approximation and with a variety of methods, although it took quite some time to understand, to get good results, because in the beginning, we were obtaining results that seemed good, but they were not really. And over time, over 15, 20 years, people came along with other methods that did better job of training and got much, much better results. This is also goes to show that, one of the problems in training, you never know if you have succeeded in training a particular cost function well. You get results that seem reasonable, but how do you know that with a better training method or with more data, you're not going to get a much better approximation? Okay, I'll let you read about the history of this Tetris game in your textbook. Now, the preceding two, in the preceding slide, it was possible to, just by looking at the problem, it was possible to figure out some good features. Now, what if you don't know any features at all? Well, that's where neural networks come to rescue. The big advantage of neural networks is that they self-compute features. They don't need externally given features. So what's a neural network? You know this figure here. What it will do is, given a state, it will provide a cost approximation. And it does this as follows. The state is encoded into a vector y of x that's suitable for processing through the neural network. This vector is linearly transformed through this layer, the linear layer, by multiplication with a matrix A and adding a vector B. Now, this A and B are tunable parameters, okay? And each scalar output of the linear layer is nonlinearly transformed by going through some kind of nonlinearity, a sigmoidal or a ReLU, or the output of the nonlinearities are linearly weighted with a parameter vector C to give you a cost function approximation. So in the end, what you have is a weighted sum of quantities which you can view as features. These are the features that the neural network has constructed by using the data, by using data, and then online they can be used to obtain cost function approximation. Now, the tunable parameters here are the parameters of the linear layer and also the parameters of the final linear weighting layer, this C. So it's A, B, and C. That's our R. And this neural network involves a single layer. Nowadays, people use many more layers. Deep neural networks have tens and hundreds of layers and many, many weights. And with multiple layers, this linear plus nonlinear portion is replicated many times, okay? This gives you a much richer architecture, which has a lot of interesting properties. And with the advent of very powerful computers, it has been at the forefront of the efforts for some very, very successful applications. Okay, so we have an architecture for cost approximation. How do we train it? Well, a major method is to collect training pairs, state, and cost function values plus some noise. So the training pairs are X of S. S is 1 up to Q. Q can be a large number of training pairs. And beta is cost function plus some noise. So we have this target function, we sample it, and we obtain this data set here. And then we determine the parameter vector by solving this least squares problem. This is a major context. Least squares regression, it's called sometimes. Sometimes a quadratic regularization term, like a multiple of the norm of the weight vectors added to facilitate the minimization, and also to deal with some machine learning related issues. If you take a machine learning course, you're going to learn that the dimension of R should not be too close to the number of data points, because that results in overfitting, where the parameters are chosen so that the R so the parameters is chosen so that J tilde is exactly the same as the target function on the data, but doesn't fit very well the target function outside of the data. Nowadays, there has been a major advance in this methodology, whereby we can use overfitting to our benefit by choosing a number of parameters that's much larger than the data set. Like in deep neural networks, you have millions and billions of parameters, and the data set may be much smaller. And you can do this through methods that match the data exactly, but manage also to provide a good approximation outside of the data set. Okay, this is a deep subject, a very interesting subject, a subject of great importance, but we're not going to cover it here. And you can find references in your textbook. Now, if you have a linear feature-based architecture, then this is a linear least squares problem and can be solved exactly by closed form expression. And here's the closed form expression, the exact solution of this least squares problem for the case where J tilde is a linear feature-based architecture. The optimal parameter value is given by this formula. Okay, there's a matrix here which is inverted. Phi is the feature vector corresponding to the state. It's a vector, right? With dimension equal to the number of features. Phi prime is a row vector, a column vector and a row vector. So each one of these is a matrix. And we are adding all those matrices over the entire data set, invert this matrix, and also compute this term here and multiply it. And that's the exact solution of the optimization problem. Now, this can be expensive and can be problematic because of the large number of features, big dimension of this matrix here, and also a big data set where there's a very large number of terms involved in this sum. So even though it's the exact solution of the training problem, it's closed form, it may not be the best way to solve the problem. And the alternative is, there are a couple of alternatives here. For the case of where we want to approximate the cost function of a given policy, there's a class of methods called temporal difference methods, TD methods. Now, some people, okay, at the beginning of the field in the 90s, for example, 80s and 90s, these were very important. They were considered as the essence of the reinforcement learning field. And if you look at the book, for example, by Sutton and Bardo, you'll see that he places a great deal of emphasis on these methods, perhaps because he was in large part the originator of these methods. But nowadays, these methods are not used very much for a number of reasons. First, they apply only to the linear case, and also they apply to a given policy. They don't deal very well with the case where you want to approximate an optimal policy. And also they apply only to finite spaces MDP. So these are historically and practically important methods in some cases, but we're not going to focus on them in this lecture. Instead, we're going to focus on nonlinear architectures and gradient methods, iterative methods for solving this minimization problem. Okay, let's abstract the problem into its essence and talk about incremental gradient methods, which are the workhorse of machine learning. Most machine learning applications use this type of method, and they apply to a problem where you want to minimize a sum of terms. Now, to make this problem more general, I denote by y the optimization variable, and we want to minimize over y this cost function, which has this structure here. It is the sum of little functions. Fi's of y corresponds to data points, basically, and each one, in typical applications, Fi's of y is the error between the ith data point and a model, okay, a parameter vector, which here we label y. So by minimizing this expression, in this context, we want to match a model to the data as best as possible according to this criterion. And each Fi is a differentiable scalar function of vector y. It may have a quadratic form, but it may not have that form. It may be, it may involve a neural network, for example. Now, a classical method for solving optimization problems involving differentiable functions is the gradient method, which is iterative and generates from a given iterate the next iterate according to a formula like this. We move from yk in the direction of the negative gradient by an amount gamma k, which is a scalar step size parameter. And the gradient of this f function is equal to the sum of the gradients of the component functions, okay? So that's the gradient method. And the problem here is that the number of terms in this sum may be very, very large. For example, think of problems that involve thousands and millions of data points. There will be thousands and millions of terms here, and thousands and millions little gradients that you have to calculate. So this is very expensive and just doesn't work. Instead, there's an alternative which is used universally. And that's the incremental gradient method. Okay, people call it gradient descent or stochastic gradient descent. I call it incremental gradient. The reason is that this method uses gradients, but it's not descent. It's definitely not descent. Descent means that at every iteration, it improves the cost. That's definitely not true. And this method also is typically non-stochastic. There may be some stochastic process that's used to collect the data set, but once the data set has been collected, this method is perfectly deterministic. So the stochastic term doesn't quite match. I call it incremental gradient method because it uses increments involving only one or maybe a small subset of terms here. So here's the typical version. We choose an index and move in the direction of the corresponding gradient of the direction of the negative gradient of the corresponding component. So choose ICAL, okay, calculate the gradient of the corresponding term, and make a move in the opposite direction with a step size gamma k. Now, the amount of overhead between this iteration and this iteration are like night and day, okay? Because this one requires computation that's proportional to the data, to the size of the data set. Here, there's only one term. It's much cheaper iteration. And however, I'm going to show you in the next slide that it still works, even using a single term. Let me also note that over time, people in the neural network community particularly have been very inventive at improving these methods. And one modification that has worked very well is to use diagonal scaling. Diagonal scaling means that you use a different step size parameter for each component of the gradient. So if this gradient has 100 components, there's 100 different step sizes that multiply the corresponding terms of the gradient. You may have heard of the Adam software. It's a very inventive, very creative method for finding diagonal scaling parameters and has worked very well in practice. There are precursors of this, but the latest is this Adam software that's being used quite widely. Okay, so let me now go to the explanation why this method works much and is also much cheaper than this method, which in practice does not work. Here an example. I understand these methods through this type of example, and this example was given in the 1996 neurodynamic programming book. Let's consider the case where y is a scalar and each of the components of the sum is a quadratic. So a quadratic in y with coefficients ci and bi. So each one of these terms has this graph, okay? And each one of these terms has a minimum that lies within some region of the real line, okay, from the minimum to the maximum. Now, the minimum of the sum is somewhere in here. We don't know it, but it's somewhere in here. Now, suppose that you have an iterate, yk, that's somewhere far to the right, somewhere over here. Then, no matter which quadratic you choose to iterate on, you're going to be moving in the right direction, right? I choose this. When I'm here, I move in this direction. Any one that I choose, I move in this direction to the left towards the global minimum. Similarly, if you are in the region far out to the left, then no matter which you choose, you move in the right direction. So within these blue regions, far from convergence, the incremental gradient method is as fast as the ordinary gradient method, but only a small fraction of the work, 1 over m, where m is the number of terms. Now, once the method, however, gets inside this red region, the region of the minima, which I call the region of confusion, it gets confused. It doesn't know in which direction to go. Let's say the global minimum is here, and we are over here, but we happen to choose a function that lies to the left, to the right. Then we move in the opposite direction. And if we choose the wrong function, then we will move away from the global minimum rather than towards it. So the method gets confused, it oscillates, and doesn't know where to go. Now, there are theoretical methods to fix that by reducing the step size appropriately. On the other hand, neural network people don't do that. They just reduce the step size up to some positive floor, and after that, they let the method run with a constant step size. Near convergence, the method oscillates in a neighborhood around the optimum, but that doesn't matter. Very often in these cost function approximation problems, you don't care about getting the exact optimum. All you care is being in the right neighborhood, in the neighborhood of the optimum. So this figure now, you can draw more general figures, you can generalize this rationale, but that's the basic idea. Far away from the minimum, choosing just one term gets you in the right direction. Close to the minimum, you may be oscillating, but that doesn't matter. And that's the key why this method succeeds. Are there any questions here? Yeah.
A particular function, there is a quadratic function, there would be one minimum. Why is it oscillating at 360?
Yeah, each one of these quadratic functions will have one minimum, but the sum, okay, the sum is somewhere in here. Okay. We're interested in the minimum of the sum. Okay, so after approximation of a target cost function, let's go into approximation of a target policy. Okay, here's one context: learning from an expert, a human expert or a software-based expert. So suppose that we have some software or some human that has a policy, can choose a good near optimal control at any state. And we want to emulate that expert. So we view mu hat as the target policy. And we collect data from the expert and then try to do some optimization, parametric optimization. So we form a sample set of state control pairs from the expert, and we introduce a parametric family of policies that depends on, it should be X here, that depends on a parameter R, and we obtain R by this least squares minimization. Now, for this to make sense, the control space should be continuous because, okay, gradient methods require continuous variables to optimize against. And otherwise, mu tilde should be a randomized policy. And this approach is called supervised learning from an expert. Has been used in a number of contexts, in games, backgammon, chess, robotics, and so on. And it can also be used to initialize other methods that are more powerful. For example, to construct a rollout policy. So that's one possibility. Here's another possibility: policy approximation on top of value approximation. Suppose that we have an approximate cost to go function that we have obtained by using approximation in value space. Now, this defines a suboptimal policy through one-step look-ahead minimization, right? We have J tilde. This defines a policy, which we'll call mu hat. You can use one-step look-ahead or multi-step look-ahead. And we view this mu hat as the target policy. And we want to approximate this target policy. In other words, we want to approximate the one-step look-ahead policy rather than do online minimization of using the cost function approximation. So what do we do here? We approximate mu hat using a training set. We generate a lot of sample pairs of states and controls from this minimization. We introduce a parametric family of policies, and then we obtain the parameter by this least squares minimization. Now, the advantage of this is that we don't have to do one-step look-ahead or multi-step look-ahead online. We can use mu hat instead, the trained mu hat instead, which is much, much faster. But there's a disadvantage also. The training is going to be done for a given cost function, given dynamics. If this change over time, like in an adaptive control context, then the training that we have done cannot be used anymore. This is trained against a particular model of the problem. If the model changes, then we have to retrain online, but that's very difficult. So that is the disadvantage. It does not deal well with online replanning. Okay. So let's talk about approximation of a target policy. We mentioned that for continuous controls, we can use the same techniques as for cost functions, incremental gradient methods, and the like. Now, if the control space is finite, there's an alternative approach that's possible. By viewing a policy as a classifier, in other words, a function that maps X into a category, mus of X. And some classifiers, we may consider this within a non-randomized and a randomized policy setting. And using randomized policies is actually more convenient in dealing with most classification algorithms. And the output of the classifier are the control probabilities, where mus of a particular U as a function of x and r gives the probability of using control u at state x, quote unquote. And the idea here is that randomized policies have continuous components, and this helps algorithmically with classification algorithms. And here's the diagram that I showed earlier. The target policy, we generate training data, and the classifier software computes a parameter that in turn can be used to generate control probabilities for any x. And then you can select a single control by using a maximization operation. In other words, at x, you generate these control probabilities, and you choose the control that has maximum probability. These probabilities encode the likelihood that the corresponding control is the optimal one, or is the one of the target policy for that particular state. Okay, are there any questions? So we talked about the first context, approximation of a target cost function. Second context, approximation of a target policy. And when we come back from the break, we're going to talk about the third context, which is direct policy optimization. So let's take a break. Okay, let us get started. We talked about the three learning contexts: target cost function approximation, target policy approximation, where we're given a policy we're trying to approximate. Direct policy optimization is what the name says. We optimize over policies, a parametric class of policies. We try to find one that optimizes the cost function. So let's go into this subject. We parameterize policies with a parameter vector R. Given the state and given R, it generates controls and generates costs. And each parameter value R defines a stationary policy, mu tilde, with cost J mu tilde of x0 for a given fixed initial state. And the policy optimization is to determine the parameter with the policy within the parametric class that optimizes this cost for this initial condition. More generally, we may consider a probability distribution over initial conditions and minimize the expected value of this over the probability distribution. And this problem has received a lot of attention because once you find a policy in this manner, you can directly plug it in to your system online, and it will generate controls. So very fast. And it has scored quite a few successes. We'll find out that there are quite a few problems with this approach. And the methods that are used for solving this problem is forms of incremental gradient methods and also random search methods. So we're going to review these two, starting with random search. Generally, random search methods apply to the general minimization problem of a function f over a parameter vector r subject to constraints. Now, this f can be very general. R may be a discrete vector, like in integer programming, for example, or it may be a continuous vector. This method generates a parameter sequence aiming each time for cost reduction. So given Rk, we generate points in some random fashion within a neighborhood of Rk, and some new point Rk plus 1 is chosen within this neighborhood aiming for better cost. Now, in theory, these methods have great convergence properties. You can prove theorems that they converge with probability 1 if you given sufficient time, like days and months or lifetime, they will converge. On the other hand, in practice, the rate of convergence can be slow. But this may be okay because the training is done offline, right? So sometimes they will work within your time limits. One advantage is that they are not affected as much by local minima. Their convergence guarantees are global, okay? They are not focused on finding a local minimum like gradient methods are. Random search looks for the global minimum. They do not require that f is a differentiable function. They don't require the existence of a gradient. And they apply to discrete as well as continuous minimization. And there are many methods and variations of these methods. And I'm going to give you some names here. Evolutionary programming, also called genetic algorithms. Taboo search is another popular method in some quarters. Simulate annealing. And a method called cross-entropy, which I'm going to describe in the next slide, has been used with success in some reinforcement learning contexts. Okay, the cross-entropy method. Remember, this is an iterative method. From Rk, it obtains Rk plus 1, then Rk plus 2 within the parameter space. And at the current iterate, we construct an ellipsoid, Ek, centered at Rk. And then we generate a number of random samples of Rk and the corresponding costs. And some of the samples are going to be good. They're going to have low cost. Other samples may not be good, may have high cost. We select some of the low cost samples, a subset of samples that have low cost, this green here. And then we move to the sample mean of the accepted samples. We move somewhere in the middle of this ellipse here. And then we construct a sample covariance, this ellipse here. We enlarge it, perhaps, and then form a new ellipsoid, Ek plus 1, by using this covariance matrix. And we sample some more within this ellipsoid. Then do the same thing. Select the good points within this ellipsoid, move to that, move to the center of that, construct a new ellipsoid, and so on. This has good global convergence guarantees, but limited convergence rate guarantees. And it may be slow, and success often depends on specific domain-related insight, and also heuristics. But it's a simple method, and it has worked in many contexts. Also, it resembles a little bit a gradient method, because Rk plus 1, by definition, corresponds to samples of low cost. So basically, from Rk, we move in the direction of improvement of the cost function, like gradient methods do. But we don't explicitly use a gradient, some kind of a sampling-based cost improvement. Okay, so that's all I'm going to say, give you a flavor about these random search methods. Now let's go to policy gradient methods. They also apply to the generic optimization problem of minimizing a function f of z. The variable is z. Z could be discrete, could be continuous. And the first step here is bold and unusual. We convert this problem to a stochastic optimization problem. This is a deterministic problem. We convert to a stochastic optimization problem where z is viewed as a random variable now. P of z is a set of probability distributions over z. Little p is denotes the generic distribution. And the expected value over p is the usual expected value. Z is a random variable probability distribution p. We take the expected value of the cost. So basically, we start from a deterministic problem, and we randomize the variable and construct a randomized problem where the variables are probability distributions. Now, if this optimization problem has an atomic distribution as a solution, namely one that's concentrated in a single z, then that would be an optimal solution of this. But generally, this problem may have lower cost than this because we're considering randomizations of the variable. So from here to here, that's a big step. However, it serves to make the problem continuous over probability distributions. And now we can consider parametrization of the probability distributions. We restrict attention to a parameterized subset of probability distributions that depends on a parameter vector R. And then we optimize over R. Okay? So from the original problem, we go to a randomized problem and then a parameterized problem, which we'll try to solve with gradient methods. So here's the original problem. We have converted it to an expected value problem, and then we approximate that with a parameterization that involves probability distributions that depend on a parameter. And this minimization may involve constraints that have to do with the fact that P sub z and R are probability distributions. Sometimes the parameterization is done using a so-called softmax reparameterization to remove the constraints. And I'm going to explain this reparameterization a few slides later. So now we use a gradient method for solving this problem, and it takes this form here. From RK, we go in the direction of the negative gradient of this cost function by a step size gamma k. And there's a key fact here. This gradient can be computed with a useful formula that allows an incremental operation. This formula involves the gradient with respect to R of the natural logarithm of the distribution P. Okay, so this is a function of Z and RK. We take the logarithm of that, and the gradient, okay, the expression for the gradient involves this logarithm. Okay, this is a fundamental fact in these policy gradient methods, and here's the derivation. That's what we want to calculate, and we view this expected value as a weighted sum of the probabilities times the corresponding values of F. The gradient of this sum is equal to the sum of the gradients, right? And the gradients with respect to R, so this is a constant as far as R is concerned. And in this expression, we'll multiply and divide with P sub Z of R at RK. It's the probability of Z given the policy that corresponds given RK. So these are probabilities that weigh these terms here. So this can be written as the expected value of this term. And if you look at this ratio here, is the gradient of the logarithm of P as a function of Z and RK. So from this formula, we went to this formula, and something magical has happened. The order of expectation and gradient has been reversed. So here we had gradient of expectation. Here we have expectation of the gradient. And this allows us to use an incremental gradient method, whereby instead of calculating this expectation fully, we just take a sample or a few samples and use them to go in the opposite direction as in incremental gradient methods. So this is the incremental gradient method for solving the problem. At RK, we obtain a sample, ZK, according to this distribution. So RK, we have this distribution, we obtain a sample, and then we compute the sample gradient, and then we use it to iterate according to this. So we don't have to compute the expectation of the thing, only one sample suffices. Okay, so this applies in general. For any problem, any optimization problem, you can do this. In the context of a discounted dynamic programming problem, Z is the infinite horizon state control trajectory, and we want to find a policy that gives you good trajectories. So we consider parametrization of of policies, randomized policies with a parameter R, and this gives you the probability distribution over Z. So for a given R, the state control trajectory is a random trajectory for this probability distribution, and the cost corresponding to this trajectory is the standard dynamic programming cost, discount dynamic programming cost, and the problem is to minimize the expected value of this as with respect to the probability distribution that corresponds to the parameter R. So the incremental gradient method is like so, and this is the gradient that you need to use. It's a sampled gradient that corresponds to a sampled trajectory zk, sampled with respect to these probabilities, to this probability distribution that correspond to rk. And you can calculate, it turns out, this logarithm in a dynamic programming fashion using summation. And I'm not going to explain this, it's a little complicated. You can find the explanation in the textbook. But that's the way this method is applying dynamic programming. For a given RK, you generate a sample trajectory, you calculate the corresponding sample gradient, and you move in the direction of that gradient. Okay. There are a number of implementation tricks that people have used in this context. You've heard about the PPO method, transregion methods, things like the use of baselines. It requires a lot of skill and a lot of luck to make this method succeed. And let's note some unusual aspects of this method. If you look at the algorithm, it involves the cost function of the discounted problem, but not its gradient. In fact, the cost per stage may be non-differentiable. Okay, that makes you immediately suspicious. It's a gradient method that doesn't take into account the gradient of the cost function. In fact, there may not be a gradient of the cost function. That seems a bridge too far, okay? The problem that's solved is continuous in order to allow the use of gradient-like methods, but the original problem can be discrete. So for example, the dynamic programming problem that you solve may have a finite number of controls, okay? It's a discrete problem. Yet you calculate, you treat it as if it were continuous through randomization, okay? That again seems to pose some kind of challenge. And finally, the randomized policy version of the problem, after you randomize the problem in the way that I've discussed, it typically has an extremely difficult structure for the use of gradient methods. It may have a concave cost function. So think of using gradient methods to minimize concave functions. And it may have many, many local minima, particularly with neural networks, zillions of local minima. So where does the gradient method go? It's an issue. So let me give you an example, a simple example, the simplest possible example that you can find. This is an alpha discounted two-state example. And we're going to use a single parameter. Single parameter, it involves two parameters, but we're going to compress them into a single parameter. So here's the problem. There are two states, left and right. And the costs, okay, the policies are to move from left to right or stay where you are. Again, from right, move to left or stay where you are. Two actions, two states, and the cost of the transitions are what you see here. Going from left to right has a cost of 2. Staying at left has cost of 1. Staying at right has cost 0. Has cost 0. Going from right to left has cost 2. So this is a very simple problem to solve. What's optimal is to go to this good state that has 0 cost, right? And go there as quickly as possible. Go from left to right, and at right, stay where you are. assuming that the discount factor is greater than 1/2, it's not too small, then this is the optimal policy. Now let's consider parametrization with a single parameter, so that R, so that from left you go to right with probability R, or you stay at left with probability 1 minus R. And you use the same probability for staying at R and 1 minus R to go to the left. So R probability is the probability that takes you to the right. 1 minus R is the probability that takes you to the left. And now we can formulate the cost function and plot it. It's a function of a single variable. And note that R equals 1 gives you the optimal dynamic programming policy. R equals 1 takes you always to the right. Okay? So this parameterization contains the optimal policy. On the other hand, let's look at the cost function corresponding to this problem. What you see here is R, the value of R on the horizontal, starting from 0 to 1. And you see the cost function as a function of R for various values of the discount factor. So this is for 0.8, alpha equals 0.8. This is for alpha equals 0.9. This is for alpha equals 0.95. So what you see here is that the cost function is concave. And what we want to find is the minimum over R. And there are two minima. R equals 0 and R equals 1, which happens to be the optimum, right? So how will the gradient method go? Well, if it starts over here, it may go down this way, okay? If you start over here, however, it may go down the other way. Moreover, because there is randomization, you may start in the good region, but through luck of the draw, by moving back and forth randomly, you may enter the other region and go over here, okay? So here's an example, a two-state example, and this is, you have this horrendous optimization. It looks more like a random search, like you start at different random points and then hope for the best, okay, rather than a gradient optimization. Now, another thing to notice here is that this is really a constrained optimization. R takes values between 0 and 1. So you have to modify the gradient method so that it takes into account the constraints. The way to avoid that is by using this softmax approximation, which I'm going to show you in the next slide. Are there any questions about this example? Is it clear? Okay. So with a softmax operation, we parameterize the problem with the idea of eliminating the probabilistic constraints between 0 and 1. So that if we eliminate these constraints, then we can use an unconstrained gradient-like method, which the policy gradient method is, the way I presented it anyway. So in place of R and 1 minus R, we use two parameters, R1 and R2, that are unconstrained, and R is reparameterized like so. E to the R2 divided by ER1 and plus E to the R2. So this is positive between 0 and 1. This is between 0 and 1. Similarly, 1 minus R is between 0 and 1. It's the corresponding the complementary probability. So now you have converted the problem, instead of minimization over R, we have converted it to an optimization over R1 and R2 that's unconstrained, okay? So let's plot the cost function as a function of R1 and R2. And here what you have. Here's R1 ranging from positive values to negative values. Here's R2 from negative values going to minus infinity, going to plus infinity. And this is the plot of the cost function. Now, the optimal policy is R equals 1, but under reparameterization, R1 is minus infinity and R2 is plus infinity. So the optimum here is out over there, okay? There doesn't exist an optimum. Similarly, there does not exist a local minimum over here. There are no local minima for this problem. There are some local maxima, perhaps, what I see here, but there are no local minima for this problem. So what will the gradient method do? Well, it may find itself over here somewhere, and then it will calculate zero gradients, essentially. So it will just stop somewhere in this region. And then if it goes in here, then the gradient is almost zero over here. So effectively, it will stop right around there. If you were to do with infinite precision arithmetic, the calculation, it will go off to infinity this way or go off to infinity that way. Now, okay, doesn't look very promising now, does it? It's the simplest possible example that you can find. When you're using a neural network, it's far worse, far worse. And you start from different starting points, and you see this policy gradient method go to one local minimum, or what seems to be like a local minimum, or go in other places with you change the random seed, and then it converges to a different place, and has all this behavior that will freak you out. Okay. So how do we compare these policy gradient methods with random search? Okay, both policy gradient and random search aim at cost improvement at a parametric policy. Both methods are slow. Random search is slow inherently. Gradient methods are also slow, although there have been some improvements in that direction by using scaling, so-called natural gradient methods, which has been incorporated in methods, trans-region methods, the PPO, and these are the most successful of policy gradient methods, but still they are slow. The use of a natural gradient has improved the convergence rate, but still the method is slow. On the other hand, that's okay. If these methods are slow, that may be fine because they're offline training methods. You can afford to spend some time using them. To make policy gradient methods work in practice, you need to randomize the starting parameter, use different starting points. So in that way, it can be viewed as a form of random search. In my mind, it's more like a random search than a gradient method. You may make up your own mind about how you want to view it. These methods, by the way, have been very successful in practice, okay? Which says something about the status of reinforcement learning. You may use methods that don't work always, but through intuition, through creativity, you may make them work for your problem. And that's all that counts. I can give you all the counterexamples you want about these methods. They look horrible, but if they happen to work on your problem, through randomization, through intuition, through good starting points, through whatever trickery you can think of, then that's fine, okay? That may be fine. That's the state of the art in reinforcement learning. If it works on your problem, it's okay, and it doesn't matter that it may not have strong theoretical properties. Okay, let me go to another difficulty having to do with approximation in policy space. It is all training and no online play, okay? Because you train a policy and it's very fast, it gives you controls right away. Very fast online computation. On the other hand, it does not adapt to changes in the problem's parameters. If you have an adaptive control setting and the problem changes on you, the cost function or the system equation changes on you, then whatever training you've done before goes wasted. You've trained for a different problem. The problem has changed on you, and a policy gradient method or a policy optimization method cannot deal with that. So it may not work well in adaptive control contexts. And also, there's another disadvantage that's kind of more subtle. We mentioned that online look-ahead minimization has very good performance properties because it relates to Newton's method. Policy gradient does not do a Newton step. Inherently, it has less, its performance inherently is worse than online one-step or multi-step look-ahead minimization. It does not involve a Newton step. So you can expect that kind of degradation in performance. And approximation in value space and rollout may work much better, and it's worth thinking about the AlphaZero context. If you try to apply a policy gradient method in AlphaZero, you'll not get a good player. It's going to do very poorly. So you may consider why that is so. Because in AlphaZero, you can do multi-step look ahead, you can do approximation in value space, you can do Newton's, things that are related to Newton's method. You can't do things like that in the context of policy optimization. On the other hand, policy optimization and gradient type methods have worked well in major applications like DeepSeek. You know about DeepSeek, right? Its policy has been trained by using approximation in policy space, essentially, an incremental type of methods. So, okay, so whatever works, and if it works, I can't argue with success. Okay, we have reached the end of the class, and just a few remarks. Some words of caution. There are challenging implementation issues in all approaches that we have discussed, particularly the ones that involve offline training, and there are no foolproof methods. That's a general statement about reinforcement learning. No foolproof methods. The training algorithms that we have discussed today primarily are not as reliable as people will have you think. If you read the literature, people talk about in glowing terms about their successes. On the other hand, they don't tell you anything about the failures or how long it took to get to the results that they came up with. Recognizing success or failure can be a challenge. You have a method that seems to work, gives you some results, you look at them, they look reasonable, but how do you know how close to optimum you are? There's no way to recognize how close you are to the optimum and whether you have succeeded or failed. I mentioned earlier this Tetris example, where for a long time, people, including myself, thought that they had very successful methods that were scoring pretty nicely. And then 15 years later, other people came along with different methods and got much, much better results. And our results looked like a failure in retrospect. We didn't know how close to optimum we were. That's the challenge. Okay, here's another thing to keep in mind. There have been spectacular successes of reinforcement learning in game context, like AlphaZero, backgammon, and other games. However, they have benefited from perfectly known and stable models. In chess, the model is known, right? It's not subject to any uncertainty, and it doesn't change on you. Moreover, many of these games have a relatively small number of controls per state, a finite number. Like in chess, there are 30 moves or so for each position. Continuous control problems have an infinite number of controls, or they may have a very large number of controls. So keep this in mind, that when you look at the successes, you have to look at the context as well. Problems with partial state observation, POMDP, they still pose a big computational challenge. There are interesting problems in this domain, but the progress has been substantial, yet somewhat slow. Approximation in value space, which we have focused primarily in this course, has its problems, and that is long online computation, right? Do one-step, multi-step look ahead, roll out, that takes a lot of computation online. On the other hand, approximation policy space does not deal well with online replanning, as we discussed. Moreover, it does not involve a Newton step, which puts it at a disadvantage. So these are words of caution. On the positive side, approximation, value space, and rollout are relatively simple and reliable, very reliable. Moreover, one can use massive computational power and distribute computation to do simulation and expedite the online execution of these methods. This is a source of hope. Whether with approximation value space or approximation policy space, we can address practical problems of unimaginable difficulty. The breakthroughs here, the practical breakthroughs in this area have been phenomenal, unimaginable for those of us that got in the field like 30 years ago or 40 years ago. So there's an exciting horizon, very promising range of future applications. So that's all a source for optimism and enthusiasm. Okay, I have one more slide. After the words of caution, some quotations, words of wisdom. I don't have much wisdom to impart on you, but I'll borrow the wisdom of other people. So here are some old quotations. The book of the universe is written in the language of mathematics, like Galileo. Bear this in mind. Mathematics is at the bottom of everything, okay? The more mathematics you know, the better off you are in reinforcement learning or in many other fields, machine learning and others, because by using logical mathematical reasoning, you're going to be able to tell the difference between the characteristics of different methods and figure out more reliably what method matches your problem and which one does not. So mathematics is important, even though the trend is against mathematics these days and more towards software. Okay, a quotation from the Confucian Analects. Learning without thought is labor lost. Thought without learning is perilous. So in the language of Confucian's day, learning means knowledge or acquiring knowledge. Thought is like reflection about problems and ideas relating to problems. So the way to read this is that getting knowledge without doing reflection is labor lost. Reflecting without knowledge is dangerous, is perilous. I think that's relevant to the field, and it's worth keeping in mind. Okay, Deng Xiaoping and his quotation, white cat or black cat is a good cat if it catches mice. This is a practical field, okay? A method is good if it works for you, okay? If it works, hopefully for others, but for you particularly. So one should not rush to judgment about some methods being good, some methods being bad. Of course, there are many methods that are being proposed in this field that are outright crazy, and they are definitely bad, but there are many methods that sometimes work and sometimes do not work. Sometimes they work very well, and in others they fail miserably in other contexts. So keep that in mind. Okay, some more recent words of wisdom or quotations. Machine learning is the new electricity. Andrew Ng is one of the prominent people in the field. Electricity changed how the world operated. It upended transportation, manufacturing, agriculture, and healthcare. AI will have a similar impact. And that seems optimistic, but as time goes on, he may be right, okay? The trend indicates that he may be right. Here's a less optimistic view. Machine learning is the new alchemy. Ali Rahimi and Ben Rechtwood, two of my students at MIT, they're prominent in the field. like in alchemy, you mix a lot of ingredients, but sometimes something interesting may happen. Sometimes it doesn't work. And it's hard to predict what's going to happen because there's no science behind it. So that's what's happening in machine learning very often. We do not know why some algorithms work and others don't, nor do we have rigorous criteria for choosing one architecture over another. So bear this in mind as well. So lots of things to consider, lots of things to think about, but our course is over. And thank you for your attendance.